Kind of general behavior as that of QPSK, in as much as the kind of data rates you can have on this modulation scheme, but has the advantage over QPSK that we very abrupt phase discontinuities of 180 degree plus minus 180 degrees are avoided by trading off this factor with the factor that now you will have phase continuities every bit interval rather than every 2 bit intervals, right. Basically that is the trade off that we have got between OQPSK, offset QPSK and normal QPSK. Both will give you the same kind of performance in terms of what we call the spectral efficiency, that is data rate to bandwidth efficiency, data rate to bandwidth ratio, right, because for every 2 bits you are transmitting one of these 4 possible phases, right. So you will have the same kind of bandwidth efficiency for both, with the advantage for QPSK that its spectrum will be perhaps slightly narrower as compared to the spectrum of QPSK signal, which has very wide, very fast fluctuations at every 2 TB seconds, T sub B seconds. Now we will now look at a variation of OQPSK called minimum shift gain. It's a very popular variation of QPSK, OQPSK, in that whatever little problem you still have with offset QPSK in terms of phase discontinuities or phase jumps that occur are completely removed in this version of the scheme. As to why it is called minimum shift gain, there is a different reason for which we'll discuss slightly later. Right now we'll only discuss it as a variation of offset QPSK. Actually this name does not come from its similarity with offset QPSK. This name actually comes from its relationship with frequency shift gain, right. So we'll talk about that name, the significance of this name slightly later. Right now let's see what it is all about. Basically it is the same thing as offset QPSK in some sense, except for a minor difference, and the difference is that unlike the offset QPSK, in which basically the baseband pulses we are using were rectangular pulses, here we use cosine shaped pulses, half cosine shaped pulses, right. So we take, this is obtained by choosing your baseband pulse waveform ST, S of t, as the so called half cosine pulse, which is defined as follows. It is equal to cosine pi t upon t. Now this capital T is the symbol interval, right, which is twice the bit interval. So t is equal to 2 TB. This is equal to cosine pi t by capital T for mod of t less than or equal to t by 2. It's equal to 0 elsewhere. So what kind of pulse shape is that if you were to plot it? No, that's all. It's a cosine pulse shape. One lobe going from minus t by 2 to plus t by 2, right. So this is the shape of your ST instead of the rectangular shape that you use in the offset QPSK, right. In the offset QPSK the incoming bit stream is separated into the I and Q bit streams, if you remember, and these are represented by sequences of rectangular pulse trains which are offset with respect to each other by half the pulse width, right. Now the only difference is we will replace those rectangular pulses with this kind of a pulse shape. Everything else is same. The incoming bit stream will be split into I and Q streams, which will be in turn represented by pulse shapes of this kind which are mutually offset with respect to each other by half the pulse width, right. So if the incoming bit stream pulses are like that, if the I bit streams are like that, and the Q bit streams will be similar in shape except that they will be offset by T by 2 or T sub B. So, and if you the resulting, this thing is called minimum shift gain. I think I best illustrate this by means of this picture here for minimum shift gain. Here the treatment that I have given mathematically, or the representation I have talked about mathematically, is a baseband representation, whereas this is a proper passband illustration of the same idea. You start with a carrier, right, of whatever frequency, because we are now talking of the passband picture, and you have your incoming bit stream divided into two parallel bit streams, one the I stream, the other the Q stream, right. Each of these streams is being represented by positive and negative pulses of this kind, right, depending on the particular bit sequence you have. These dotted envelope lines that I have shown here, right, this one here and this one here, the sign of these dotted lines, that is, this is a positive sign, means perhaps the I bit here corresponds to a 1. Here also the I bit corresponds to a 1. Here it corresponds to a 0. Here it corresponds to a 0. And this interval is, let's say this, I will choose my reference as 0 here. So this is minus T by 2 and this is T by 2, right. So this and so on. In the quadrature bit stream, same kind of pulses appear here, but of course the bit sequence can be totally different from the corresponding bit pattern in the I bit stream, because the two bit streams are basically representing alternate bits of the incoming bit stream. Alright. So in the Q bit stream we have a 0 followed by a 0 followed by a 1 followed by a 1, right, and obviously they will be represented by these kind of baseband pulses. And how do you do the actual modulation, actual passband modulation? What is the mathematical mapping which takes you from baseband to passband?
How do we get the envelope, whether it is to be upper one or the lower one?
No,
what means I stream?
That comes later. Envelope actually, in fact, in the first instance, just ignore what is there inside. In the first instance, think of this dotted lines as the positive and negative pulses corresponding to the ones and zeros that are coming in that particular bit stream. It is from starting from these pulses that we will go eventually to the modulated waveform, right. So ignore the modulation, the carrier in between to start with, right. So to start with, you only have this positive and negative pulses. In the I stream, similarly positive and negative pulses in the Q stream corresponding to some input data stream. Alright, is that fine? Can we proceed from there? This, how do we convert this into a passband waveform? By multiplying this with the cosine carrier and multiplying this with the sine carrier, right. By multiplying the I bit stream or I pulses with the cosine carrier, that's what it is. Suppose, well, one phase of the carrier, this is actually the other way around, this I have shown as sine modulation and this has cosine modulation, it does not matter which way you do it, and the resulting waveforms will now be as shown over here after modulation by multiplying these pulses with the corresponding carrier. Of course, the carriers in this and in this are mutually phase shifted by 90 degree because they have to be quadrature carriers. One has to be cosine, the other has to be sine. Right? Now, if you sum them up, that is your final passband modulation. I cosine omega ct plus Q I cosine omega ct plus Q sine omega ct. Right? You add these two up, you will get your final modulated waveform, which now looks like this. and what do you see?
Continuous phase.
There is absolutely no phase transition anywhere. Phase transition anywhere, right? You will find that at each bit interval there is a absolute continuity of phase from one bit interval to the next bit interval, right? This is the physical picture. Now, before I go into the mathematics and illustrate or demonstrate to you that such a thing should happen mathematically, can you see what is happening physically here from the picture? Why there are no phase transitions? Although we are doing things in almost exactly the same way as we were doing in the case of offset QPSK. How does how do we avoid certain phase jumps in this case? By just changing the pulse shape. The basic thing that is happening, if you notice, is that instead of, see what was happening in OQPSK, at every bit interval a new data bit was coming along in either the I channel or the Q channel, which was causing a phase jump of pi by 2, right? Either plus pi by 2 or minus pi by 2, right? Now that phase jump is replaced by a continuous phase change over the bit interval. Instead of there being a phase jump just at that instant, that if equivalent amount of phase change is actually obtained through a gradual process of phase change over the bit interval rather than suddenly at the bit transitions. That is the essential difference, and that is brought about by these envelope modulations, by this, right? In fact, if you notice it carefully, take this bit interval, you will find the way I have plotted it, exactly 2 cycles of the carrier. Take the next bit interval, you will find a different number of cycles. In fact, you will be able to see that one can discern in each bit interval the presence of one of 2 possible frequencies of the carrier, right? As if the carrier is not a fixed frequency carrier, but you are shifting from one frequency to another frequency, from one bit interval to the next bit interval, because continuous phase change also implies a frequency modulation, right? A continuous phase change implies a continuous frequency change. In fact, one can see that this final modulated waveform can also be thought of as an FSK waveform, as a frequency shift keyed waveform, right? Because in every bit we will have one or the other of 2 possible frequencies, which we will see, right? So this is a physical picture. If it is clear, then we will go into some mathematics.
Why is the frequency difference taking place?
We will see that mathematically. It's better to appreciate that mathematically. But as you can see, sometimes intuitively I can tell you why it is happening. Let's get the intuitive picture right. You remember in the OQ, always go back to your offset QPSK picture. In the offset QPSK case, there is a phase jump of 90 degree every bit interval, but that phase jump could be a plus positive phase jump or a negative phase jump. That means over the bit interval you would like the phase either to increase linearly constantly or to continuously decrease. When it is increasing gradually, you are having an increase in frequency. When it is decreasing gradually, you have a decrease in frequency, right? Basically that's the idea. So is that okay? Is the intuitive picture somewhat clear? Then the maths will make it further clear if this is okay. Can we proceed further? Any questions? So let's return to the maths now. By looking at some basic properties of this MSK waveform, this we'll call, in short we'll just call it MSK. The first property that I like to talk about is the fact that MSK waveform has a constant envelope. Right? Okay, that is intuitively clear here. Although the individual I and Q channels seem to be amplitude modulated DSPSC kind of waveforms. The final overall modulated waveform, MSK waveform, is a constant amplitude or constant envelope signal, right? Let's see mathematically how we can prove that. But all you have to do is look at the complex envelope of the corresponding baseband signal and look at the magnitude of that complex envelope, right? So if you write down the expression for MSK, before doing that, just what we'll assume is that we are assuming A equal to 1. Remember I said that this A is the amplitude of these pulses. Okay, we'll take the amplitude of these pulses to be 1 and prove that the envelope, which is the magnitude of the complex envelope CT, will also be equal to 1. So if we take the amplitude of these pulses to be equal to 1, then the magnitude of the complex envelope will also be equal to 1.
One of them is cos t and the other is sin.
J sin
That's
t.
right. So I think it's quite obvious. Proof is really a one-line proof. It starts by the observation that we are basically in the I and Q channels having two basic pulse shapes: the cosine pulse shape, half cosine pulse shape, and its t by 2 shifted version, which is a sine pulse shape, right? So t by 2 shifted pulse is a half sine pulse, right? That is st minus t by 2 we can write as sine pi t upon t for 0 less than small t less than capital T, right? And using this fact, going back to our expression for CT, if you recollect from our last time's discussion, we have this expression for offset QPSK. A sub 2L st minus 2L t sub b plus j times this corresponds to the I bit stream. Take the q bit stream, quadrature bit stream, or the odd bits. This will be 2L plus 1 t sub b. Can you see it there?
No, something's gone wrong.
Yes, sir. So something is gone wrong here. Sir.
So even yesterday,
So contrast is bad, sir.
so even yesterday the same thing happened.
The sine is
So contrast is bad.
Okay. Can I move around here?
So their contrast is good.
What's happened? That's okay. So can I proceed ahead, or there's still a problem?
There's a problem, sir.
Yes, sir.
Some light has to be switched off, right?
No,
Some light has to be
there's
switched
a contrast.
So the cassettes are available now?
I believe so.
Are they available in the library?
I was told that they were going to be available. I have not checked. I'll check today. I can see from here. There obviously some glare coming from somewhere.
That one the contrast is okay, but can't see that.
No, it's a. I think it's the angle at which you are sitting.
10 minutes ago it was fine. Even yesterday the same thing happened. In the last 15 or 20 minutes, same thing.
the focus
The brightness of a TV could be increased.
I am asking these directors. Okay. So let us look at the complex baseband representation of the offset QPSK, from which the MSK is derived, right? And all you have to do is substitute for this. This is a cosine waveform, cosine pulse, and this is a sine pulse. Basically, this is what you have to appreciate, right? Because this is the same pulse shape as this, except that it is shifted by t sub b or t by 2, right? And since both A sub 2L and A sub 2L plus 1 essentially are positive or negative amplitudes equal to plus minus 1, right? So we can write this as equal to plus minus cosine pi t upon t plus minus j times sine pi t upon t, right? And it's quite obvious that no matter what these signs might be, as far as the magnitude of the envelope is concerned, it's obviously going to be equal to 1, right? So that shows that there is no amplitude fluctuation whatsoever in an MSK waveform. Now that is a very, very desirable property in any digital modulation waveform, right? For reasons for which we have discussed a number of times in the last 2 classes. For example, this will make it relatively insensitive to non-linearities which may be present in your system, right? And that's a major reason for the popularity of MSK waveform in such applications, particularly let's say satellite channels where non-linearities are a fairly important class of problems to worry about. Now the second reason for its popularity comes in the second property that we are going to discuss, which I will discuss very briefly here. That has to do with the power spectrum of the MSK waveform. You see, bandwidth efficiency is a very important factor for us. The QPSK and MSK waveform modulations are very similar in many respects, but because of the fact that you are using these pulse shapes to be cosine, which have a gradual decay, not really a gradual decay, at least they don't end up as abruptly as rectangular pulses do. They have some kind of a roll of between from one bit interval to the next. The power spectrum corresponding to a MSK waveform has a sharper decay compared to a corresponding decay of the QPSK waveform or OQPSK waveform. So the half cosine pulses that you use here, they are associated with a better spectrum. Their spectral side lobes. The rectangular pulses have a sinc function as a spectrum, or if you look at the power spectrum, it is sinc square, right? The side lobes of that we know don't decay very fast, whereas the cosine pulses that we are using here have spectral side lobes which fall off as f to the power minus 2 rather than f to the power minus 1. Actually, power spectrum will fall off more rapidly, isn't it? F to the power minus 4, right? If the side lobes themselves fall off at the rate of f to the power minus 2, and this is the spectrum of the pulse, as far as the power spectrum is concerned, they will fall off even more rapidly as f to the power minus 4. In fact, one can show the precise spectral expression for an MSK waveform when you assume the consecutive bit streams to be independent of each other. Under that assumption can be seen to be given by this expression. I'm just showing this for the sake of completeness, a result which you can easily appreciate, isn't it? Because you have seen what kind of pulse shape you get if you have a raised cosine kind of power spectrum when we did the Nyquist criteria and all that, right? There we are working with this kind of functions in time. We now have a dual function in frequency, right? Because the corresponding pulse shape is a cosine pulse shape in time domain. So the results are easy to appreciate from what we have discussed earlier. So this is the power spectrum. This is not the power spectrum. This is the spectrum of the cosine pulse, half cosine pulse, right? The power spectrum will be magnitude square of this. So this is the second advantage, which I have plotted here in terms of a comparison with other spectra of other pulses. I have compared here in this picture the spectral efficiency of binary phase shift keying, quadrature phase shift keying, as well as offset quadrature phase shift keying and MSK, and you can see the relative standing of these.
So why MSK is between the two?
BPSK and OPSK.
No, it is actually better and not between the two in some sense. Yeah, we'll have to see that. It's very easy to appreciate. As far as BPSK is concerned, its spectral efficiency is poor, as you can see. Because here your bandwidth is really governed by the bit interval, right? And depending on the data rate you have, your first zero crossing occurs at 1 by 2 dB of that, right? Whereas QPSK, since you are looking at 2 bits at a time, effectively your main lobe width comes down by a factor of 2, right? For the same data rate, your spectral efficiency increases by a factor of 2. However, there is a considerable amount of energy in the side lobes, and this is what is of great concern. When you do a final band limitation, although roughly we say that the spectral efficiency is good, in practice the spectral efficiency is going to be very poor. Reason is, we are not really going to restrict the bandwidth through just the main lobe. We are going to have to restrict the bandwidth up to a point where there is significant energy in the spectrum, right? Because if we don't do that, we are going to have the other problem. Which is the other problem? Suppose I band limit it very strictly according to this main lobe width, the non-constant envelope problems, right? So one has to choose between the two.
Could you please repeat that? How do you correlate this non-constant and like I don't understand.
You see, basically, it is a band limitation which causes the problem, right? The more severe the band limitation, the more severely your sudden transitions in time domain will be flattened out, will be smeared out, and there will be therefore the amplitude variations will become larger after filtering. If you filter signals which have sharp discontinuities and you filter them very heavily, they are going to be much larger magnitude variations in the envelope than if you were to allow most of the spectrum to pass through. If you allow most of the spectrum to be passed through in the filtering process, that means you are not really carrying out much filtering, right? And therefore it will not distort the waveform too much. It will not introduce unnecessary amplitude fluctuations, right? So you have a trade-off to worry about, because there is a significant amount of energy in the side lobes in the case of QPSK and OQPSK. On the other hand, as far as MSK is concerned, there is very little energy in the side lobes. In fact, even what I have drawn here, comparatively speaking, should be much lower than what I have shown, right? As far as side lobe power is concerned. Of course, the total energy is constant. So if you remove the energy from the side lobes, it has to come somewhere else. It has to come in the main lobe, and therefore you will see that the main lobe width increases as compared to QPSK, isn't it? Because the total energy is same of the signal. So if you are taking away the energy from the side lobes, it has to come within the main lobe. Therefore you will find that the main lobe width increases, but I still now have the advantage that by just increasing the bandwidth slightly, I have most of the energy of the signal accounted for, and therefore we can expect very little envelope fluctuations or amplitude fluctuations after filtration of such a signal before transmission, right? Which is the reason why MSK is really popular in those kinds of channels. Is it all right? Do you appreciate this point now better by looking at the spectra, relative spectra of the various related schemes, modulation schemes? Any questions? Okay. The third property we will discuss is what we discussed intuitively a few minutes ago, that is MSK viewed as an FSK signal. And that's also extremely easy to appreciate. Again, let's start from the complex envelope, and a few minutes ago I showed to you that we can write this complex envelope of the MSK waveform as this kind of an expression. I wrote T there, I am replacing that with 2 T sub B. Which you can appreciate can also be written as plus minus e to the power plus minus j 2 pi T upon, I have just deliberately introduced this vector of 2 pi instead of pi and T by 4 dB for let us say T in the Lth interval, going from L Tb to L plus 1 T sub B, right. In any bit in the L plus 1th bit interval, we can write the complex envelope either in this form or in this complex exponential form, right. And of course these signs will be dependent on what specific data stream is coming along. These signs are really a function of the data stream that is modulating the carrier, and these signs will change abruptly from one bit interval to the next, because as data stream keeps coming in. Now if you can look at this, if you look at this complex envelope waveform, particularly looking at this exponent, what does the exponent tell you? This exponent j 2 pi T by 4 Tb.
What does it tell us?
Linear phase.
What kind of phase function
Linear
is this?
Linear.
It's a linear phase function or a constant frequency function. Within a bit interval, if you were to look at the frequency, which is the instantaneous rate of change of phase, right, or derivative of the phase function, is going to be a constant function, right. So within each interval, we see a frequency of either plus how much, plus 1 by 4 Tb or minus 1 by 4 Tb, right. A constant frequency of either plus 1 by 4 Tb or minus 1 by 4 Tb, right. Of course, if you were to look at this waveform in association with a carrier, that will be f naught plus 1 by 4 Tb or f naught minus 1 by 4 Tb. So that's the frequency shift keying that we were talking about, right. So this, you can read the frequencies of the complex envelope as frequency changes of the actual modulated signal finally, right. So that is the first thing that you appreciate. Let's rewrite this as this: Ct is equal to a to the power j theta t, right. If you were to write it like this, I can write an expression for theta t as follows: theta as a function of time. Now within each bit interval we know what the behavior is. You either increase linearly, the phase either increases linearly or it decreases linearly, right. That means you start from somewhere, theta sub L, which is a phase, starting phase at the previous, which was the ending phase of the previous bit interval, right. And you are now getting to the next bit interval, and from there onwards your phase is either increasing or decreasing linearly, eventually going up to. So this is the mechanism by which your phase is changing, isn't it? what is the expression between, what is the difference between this expression that I wrote here and this? I have taken cognizance of the fact that we have a starting initial phase which will dictate what is, whether this is plus or minus here, right? And then we will have right. So this plus minus sign here I have put in theta t itself as a function, right? So depending on what your initial phase was or what your ending phase of the previous bit interval was, let's call that theta L, the final signs will be decided, right? Which I am not going to the details of, which is easy to appreciate, that the sign of theta L will have a bearing on whether you will have plus here or minus here, right? Because after all you can split this up into e to the power j theta L into e to the power plus minus the rest of the function, right? So depending on whether e to the power j theta L gives you a plus, I mean it can give you 4 possible phases again.
So theta L is the previous phase.
Yes, theta L is the previous phase, right? All right. So, and I have subtracted this minus LTB because we are now looking at the phase behavior in the after LTB, after the time instant LTB, right? And from there onwards it's increasing either linearly with time or decreasing linearly with time. And to what extent will the phase change? Let's say if you put t equal to L plus 1 TB, it will go up to 2 pi upon 4 TB, right? Pi by 2. So plus minus pi by 2, which is precisely what we expected in normal offset QPSK. The only difference is, instead of that happening suddenly at that point, you have a gradual phase change, eventually culminating in a total phase change of either plus pi by 2 or minus pi by 2. So therefore we can conclude, so of course I should write here LTB less than t less than or equal to L plus 1 TB. This is the expression for the next interval like that. So we can now say theta LTB, we can broadly conclude, will be either 0 degree or 180 degree, right? Either it will be of this form. Now this is from our appreciation of the QPSK, offset QPSK signal that we have discussed a number of times before. This will be the case when L is, let's say, even, right? And it will be 90 degrees or 270 degrees when L is odd.
So we illustrate this.
Illustration will be a bit difficult, but it's very easy to argue it out. Let's say you start with some initial phase. Let's say you are starting with the odd bit case, or let's say you start with 0 phase, right? After 1 bit interval, you'll either go to plus 90 degree or minus 90 degree, right? So it will be either plus 90 degree or 270 degree. After the next bit interval, you'll again go to either 180 degree or 0 degree, right? And so on and so forth. So it's very easy to appreciate this fact. Of course, the actual values will depend on the data stream that you have. Okay, and what theta L plus 1 has to be will be dictated by the data stream, right? Only thing is, accordingly this plus minus sign will change. If theta L plus 1 has to be less than theta L, there will be a negative sign. If theta L plus 1 has to be more than theta L by 90 degrees, then there will be a positive sign. Let's proceed further with this discussion and rewrite. Now let me look at the modulated waveform with carrier. Since it doesn't really cause any confusion, I'll continue to use the symbol CT. So I'm using here sometimes CT for complex baseband waveform, sometimes for the real modulated waveform, without changing the notation, because it doesn't cause any confusion. If it causes any confusion, let me know. So the real waveform carrier with carrier can be written as, I think I put a bracket like this here, all I'm doing is appreciating the fact that the carrier is going to be associated with this phase, extra phase, right? You will have the term F naught t, of course, and this is the extra phase. You have to keep that in mind, which you can write as plus minus t upon 4 TB, right? That's the increase or decrease. Minus plus, I'm just substituting this expression. I think let me keep it here, right? Minus plus L by 4 plus theta L. All I have done is substituted this over here along with 2 pi FOT, right? So you can write the modulated signal with carrier in this form, which you can write. If I define, I already appreciated the fact that F naught plus 1 by 4 TB can be taken as one of the two possible frequencies, and F naught minus 1 by 4 TB can be taken as the other frequency. So I'll write this as 2 pi times Fi, where F sub I is the instantaneous or frequency in that particular bit interval, Fi sub into t, F sub I into t minus plus L by 4 plus theta sub L.
What is this L by 4 for?
This L by 4 comes from this, because L TB upon 4 TB, right? And that basically takes care of the fact that every bit interval you either increase your total phase by pi by 2 or decrease it by pi by 2, right? Because 2 pi into L by 4 is a final phase, right? And it is this final phase change is occurring gradually through this frequency change process, right? Basically that's what the whole idea is. Now that corresponds to F1, Fi equal to F1 or F2, that is I is equal to 1 or 2, and F1 is Fo plus 1 by 4 TB, and F2 is F naught minus 1 by 4 TB. Alright? One can also, whatever we have discussed so far, one can, this equation for theta t, theta t behaves like this with time, can be expressed in terms of a what is called a phase trajectory diagram, right? In which basically in going from, you see there is a linear, either you are increasing the phase linearly or decreasing the phase linearly. So in going from one bit interval to the next bit interval, you could be anywhere along this grid depending on the input data sequence that you have, right? Because depending on the input data sequence that you have in any specific bit interval, I mean let me take arbitrarily, you might be initially here, your theta L value may be initially here, and then you may be either increasing linearly or decreasing linearly from there onwards, right? Where all successive phase differences are pi by 2 values, and all this, I mean, if I am exceeding 360 degree here, you must interpret the phases to be modulo 360, right? So I have plotted this grid here where a typical phase trajectory, for example, could be like that, or another one could be sorry, yes, it could be like that, right? Why not? Depending on the input bit sequence that we have, there may not be a phase change from one bit to the next.
There has to be phase change always.
No, there doesn't have to be. Suppose the two bit stream, two successive bits in both the channels are exactly the same as before, right? No bit changes are required. So in that case,
We talked about an odd and even thing and said that
Yeah, I think perhaps in this scheme there has to be phase change to the extent.
What did we just now said that L is odd? so it
Yes,
will-
I think that's an important point. I'll have to think about it. You also think about it. I think there may be truth in what he says.
you talked
That-
about that one odd and
Yeah, right. There has to be a phase change, I think, but I'll have to verify it and be sure. So I think the trajectories we are talking about will avoid this horizontal path. In fact, you notice that actually these are only reference lines, so I got confused with that. So you should really either go up or go down. That's all. These are the possible phase trajectories, and so on. So these are typical MSK phase trajectories and represented in this manner. So we have seen the FSK interpretation of MSK. Now there is an interesting thought here which I'll just like to share with you. You could therefore obtain the same modulated waveform not through the modulation process that we talked about. What is the modulation process that we have talked about? Our modulation process consists of take your incoming data stream, split it into two parallel streams which are quadrature delayed with respect to each other, right? And represent the data in each of the I and Q streams by half cosine pulses or corresponding sine pulses, right? And then these half cosine pulses multiply the carrier, and these two carriers are simply the quadrature carriers, and they are simply arrayed after modulation. That's the modulation. That's a mapping process from data bits to the MSK waveform that we have discussed so far. But we could as well have carried out that modulation process through a different mechanism. For example, suppose the incoming bit was 0, right? I could have linearly, I could have associated with the frequency f1. The next bit is 1, I could have associated with the frequency f2, right? That is a decrease in phase, and so on. And that would have resulted in a similar kind of phase trajectory. As far as phase trajectory is concerned of the signal, it would have resembled an MSK waveform in terms of properties. So I'm not now splitting the incoming data into I and Q streams, just looking at successive bits, every bit interval, and associating a frequency f1 or f2 with each bit, right?
But sir, then the band would have been larger. Like,
No, because you have precisely the same waveform. As far as basic waveform properties are concerned, they remain the same, isn't it? Because you're following the same phase trajectory.
What do you mean by associating a frequency F1, F2?
So with the
Mapping, the
with
mapping
each-
of the
with-
data to the waveform. See, after all, what does a modulator do? The basic function of the modulator, don't forget about it. Its basic function is to map data bits onto a waveform. Now, we have discussed one mechanism in the context of MSK for this mapping. I'm discussing a possible different mechanism, right, in which successive input bits are associated with corresponding to each successive bit, let's say 0, I generate a cosine a carrier with a frequency of 1, right? For the next bit, which may be a 1, I generate the same carrier with a frequency f2, with maintaining the phase continuity, right? So effectively, I'll generate a waveform whose properties will be the same as that of the MSK waveform we have discussed, because MSK waveform also in successive bit intervals goes through frequency changes of f1 or f2 or f1 f2, right? It may be f1 or it may be f2. Let me physically generate those f1 f2 by associating those with actual bit values directly. I can do that. That is how it is an FSK waveform, right? You can think of this as a frequency shift keying waveform in that manner. Not clear? I don't think you're all very happy about that. Is there a doubt about this? आज के लिए बहुत हो गया.
So one thing we call it MSK. Why do you call it minimum shift keying?
Yeah, that's a question I was going to come to, but he says आज के लिए बहुत हो गया. So we'll start from here next.